All right, so now we can start talking a little bit more about those laws of thermodynamics and start talking about this concept of free energy that's going to become really important when we start talking about how chemical reactions actually occur in living systems. Okay, so what we need to do is be able to explain the laws of thermodynamics. We're going to focus on the first and second laws. We're going to take that idea of free energy and again apply it to chemical reactions. And then we're going to look at how chemical reactions occur when there's an enzyme present to when an enzyme is absent. All right, so the first law of thermodynamics, we kind of already introduced this, but we'll say it again, right? This is that energy cannot be created or destroyed. It's only going to change forms. And the total amount of energy that is available in the universe has been constant since the Big Bang. Okay, so we're not gaining any more energy. It's just shifting around in all the options. So if we add up all the energy, we're still going to have the same amount. It's just going to be put into different buckets. Okay. And again, whenever we transform some of that energy, some of it is going to be transferred as heat, which means that it's lost to biological systems because heat is not a form of energy that biological systems can use effectively. All right, so our second law of thermodynamics is really important that we understand this because this is going to play into how chemical reactions occur and why we actually need this energy processing, right? Why that was one of the elements that defines life. All right, so second law of thermodynamics says that entropy is always increasing in the universe. So what entropy is can kind of be summarized easily as disorder, right, or messiness. So the a great example of this is your bedroom, right? So some of you people have bedrooms that look all neat and tidy, and your bed's always made, and there's no clothes on your floor, and everything's always put away, and everything like that. And then some of you have bedrooms that look like me, where there's a wardrobe and there's a stack of books on your night table that you probably should read, but you don't anyway. And your hairbrushes are laying around, and right. So it's kind of like it's lived in. That's how I'm going to justify it. It's lived in, right? And the natural state of your room is to get messier over time, unless you put in energy to tidy things up, right? So it takes energy to make your bed. It takes energy to pick up your laundry and fold it up and put it away. It um, so without that energy input, right, it's just going to get messier and more and more and more and more disorder, and that's what entropy is. Okay, so like a kind of a more chemical, like another chemistry example of this is going from solid state to liquid state. Okay, so when substances are in their solid state, there's more structure, there's more rigidity, there's a tighter packing of the atoms that make up that substance. When it turns to liquid state, there's more mobility of those particles. There's more disorder, there's more variations, right? There's a lot more ways to be messy than there is a way to be neat, which is kind of what entropy is trying to kind of getting at. Okay, so messiness is the stable state, even though your mom tells you that you have to clean up your room. And being a mom, I tell my kids to clean up their rooms quite frequently. And they're like, yeah, well, maybe you should clean up your room. I'm like, shut up, kid. Don't tell me what to do. All right. Okay, so this is going to get us to our concept of Gibbs free energy. So in our biological systems, right, we need to have order, we need to have homeostasis, we need to keep things together, right? But the natural state of the universe is to increase the disorder. So we need to have a way that we are going to have our energy input to keep our cells doing cell things. Okay, so the chemical reactions that are required in order for cells to keep doing cell things is going to require that we're going to start out with our reactants at a low energy state, and we're going to end up with our products at a higher energy state, right? We're going to have energy input. We also have in our cells, we have chemical reactions where we actually release some of that energy, okay, where we're going to take those stored, that potential energy that's stored in those reactants, and we're going to release that energy so that we can then power these other chemical reactions that we need to do, right, to keep our cells in order. Okay, so Gibbs free energy, then we can define it as the amount of energy that are needed for bonds to form, or the amount of energy that is released when we break bonds. So in an endergonic reaction, we need energy input, right? We need to clean up our bedroom. And in an exergonic reaction, we are going to release energy so that we can then harness that energy for other things, okay? So let's have a closer look at this. Okay, so an endergonic is going to require the absorption of energy in order to form chemical bonds. So remember back when we were talking about monomers and polymers, right? We needed energy to put those two pieces together to form our larger biological molecule. Okay. And we talked then about those being anabolic reactions where we're building up those reactions. And these reactions are not spontaneous, which means without that energy input, these reactions would never occur naturally, right? We need those energy, that energy input. In an exergonic reaction, though, right, these are a catabolic. We're going to take our polymers and we're going to break them apart into our monomers. That releases the energy in those chemical bonds. And this is spontaneous. And remember that when we're talking about the chemical context of spontaneous and non-spontaneous, this means that it will happen eventually on its own. It's just, will the speed of that reaction happen in a time frame that's meaningful for biological systems? And usually the answer is no, it won't. All right. So make sure that you're understanding the difference between endergonic and exergonic, making sure that you're knowing that where anabolic and catabolic fit with each of those ender and exergonic reactions. Okay. And then when we get back into class on Monday, we'll do some drawing on the board to help us remember these things. All right. So whether we are having a catabolic or an anabolic reaction, we need activation energy. Okay, what activation energy is? This extra energy input that is going to take those chemical bonds that already exist and destabilize them so it's easier for that process to occur, right, to initiate that chemical reaction. And that could be, like I'm indicating here, where we're have a catabolic reaction where we're breaking something apart, or we are trying to put things together. We got to line them up, boop, so that they'll form those chemical bonds. All right, so let's talk about what this means. So here I have a picture of my dog Sadie, when she was a wee puppy, and then my youngest kid here when she was a wee lad, trying to make cookies or make bread or whatever she was trying to do at the time, right? So these, if you're a parent or of human people or a parent of the fuzzy variety, you probably know that the most alarming noise that you can hear as a parent, whether that's parent of humans or human of pets, is silence. You're like, what are you doing? You're like, God damn it, I just sat down. And now you have to go like gain that extra energy to like, get up and go see what these guys are getting, like what trouble are they getting into? Because if you can prevent the trouble, right, then you're gonna be in better shape than if you let the trouble to happen and have a mess like these to clean up. Okay. So that's kind of my analogy for activation energy. Is like, oh, you just sat down to relax finally. And then you're like, wait a second, what are you doing? And you have to dig deep, find that extra energy to get back up and prevent the mess. Okay. So again, like I mentioned before, all reactions have activation energy, whether it's an endergonic reaction, right, where we're going to take this reactant and we're going to build it, and we're going to end up with a higher energy state than what we started with. Or if we're going to take our an exergonic reaction where we have our reactants, our starting point, we need to have some energy input so that we can break that apart and have that energy be released. Okay, so the number one bracket right here, this is looking at the activation energy. So we can see that in an endergonic reaction, the activation energy is a lot higher. In an exergonic, it's much smaller, but it's still present. Okay, in our endergonic, we're using energy, right? We're absorbing energy in order to create those bonds. In an exergonic, we're releasing energy. All of this energy in this number two bracket can then be portioned off to power other processes in the cell. Okay. All right, so all reactions, whether we're anabolic, catabolic, exergonic, endergonic, all reactions have an activation energy. So we need to make sure that, right, if we're trying to maintain life and we're trying to maintain cells that have order and have homeostasis and have all those elements that are required for life, we need to make sure that those chemical reactions that are necessary for that are happening at a time scale that's important to us. So the way that we can speed up chemical reactions, so two examples are, we can heat it up, right? We can increase the kinetic energy of the particles. And so if they're banging together more often, they're more likely to initiate those chemical reactions. The problem with this is that we need to maintain homeostasis, right? And so if we need to heat up a system so much that for those chemical reactions to occur, it might be beyond what a plasma membrane can handle, for example, right? That plasma membrane might melt before we can speed up those reactions to a point that's meaningful. So we need a different mechanism because, yeah, heat it up, it'll get you only so far. So what we are going to need to do is the way that we're going to do this in living systems is we are going to lower the activation energy, right? We're going to make it easier for us to get up off the lazy boy right after we finally sat down, right? Maybe we have a spring-loaded bling ejection button that we can activate when our kids and our pets are creating shenanigans. Okay, but in living systems, what's going to do that is not an ejection button, but is an enzyme. Okay, so let's look at this chemical reaction. Here we have carbon dioxide and water, and they're going to react to make carbonic acid. So without an enzyme, the activation energy is quite high. With the activation energy, with the enzyme, the activation energy is much lower. So there doesn't have to be as much energy input. It's a lower pole vault to get over, right? So we don't have to spend so much energy pole vaulting over that hurdle, right? So we're going to lower that activation energy with an enzyme. Okay, and we can use any kind of catalyst. So organic catalysts are called enzymes. There's also inorganic catalysts that are going to do similar things, but each catalyst is specific for the reaction that it catalyzes. And so let's lay out some ground rules here. So catalysts are going to decrease the activation energy, but they cannot violate the laws of thermodynamics. We cannot turn a anabolic reaction into a exogonic or exergonic reaction, right? So we can't turn something that requires energy input into something that is going to have energy output, right? So whether we are going to have, so in this case, right, our enzyme we're starting our reactants, the things that we're starting with are starting at the same energy level. We just have to go up a small amount to get that activation energy, and then we break that. And our products, the thing that we're going to end up with, is going to be at the same energy level with or without the enzyme. Okay, So enzymes cannot make an endergonic reaction spontaneous, right? So we still need to have that same amount of energy input. It's just the activation energy is lower. And we are not going to increase, or we're not going to alter the effectiveness of that reaction. So whatever our reactant is, and we're going to end up with the same amount of products at the end. Okay. So here's a question that I had on my exam for my other class, and the students, most of the students got this question wrong in the same way. So I wanted to throw it out to you guys and see what you guys think. What is the role of enzymes in metabolism, right? And all these chemical processes that are required for cells to stay alive and do cell things. Are they going to A, increase the amount of energy released by the reactions in catabolic reactions? Are they going to speed up chemical reactions by lowering the activation energy? Are they going to provide energy directly to drive metabolic reactions and in anabolic processes? Are they going to stop reactions once we have enough product? Or are both A and B true? Okay, I'm going to ask you guys this question, so I'm not telling you the answer right now. Okay, and I also want to throw this practice essay question out to you guys. Okay, this is actually, I yoinked this straight from your book, but I thought that this was going to be a good option for you guys to practice thinking about how to write a paragraph and how to make sure that you're answering all parts of an essay question. So I would ask, if this was on an exam, I would ask a question similar to this. I would have it worded a little bit differently, of course, but I would say, can an enzyme make an endergonic reaction exergonic? And in this answer, I should expect you to be able to define ender and exergonic reactions. I'd expect you to be able to tell me about Gibbs free energy for both exer and endergonic reactions. I want you to be able to define enzymes and talk about how enzymes affect chemical reactions. Specifically, you're going to talk about their activation energy and how enzymes affect that activation energy, right? But not other properties of the chemical reaction.